Hello YouTube, today we're talking about SPI, serial peripheral interface. It is a bit different than I2C, only similarity that data going on one wire and there is clock. But the difference is that there is two wires plus clock. Somebody call it three-wire interface. There is actually fourth wire, which is slave select, but not selecting like a chip select when signal is 1. It is not slave select, NSS, so opposite. Selecting is by putting 0 on this wire. So when, for example, we have two sensors, our microcontroller wants data from one sensor, it put 0 to this chip select or NSS pin, then sending data request, then in the same, almost in the same time, getting data back, then pulling wire back up to high voltage, then select another one by pulling wire down, the same thing with another sensor. Or if we have microcontroller, we can send data. Not sure how it goes. I think that this video will be relatively short because I want to split into few videos. Reason being, it is a little bit complicated to put everything in one video, and I have no right now assembled anything except one transceiver SC4432. I want to talk about that one. Excellent stuff. Next time I will probably connect two microcontrollers to see what is happening by using logic analyzer. Let me try to show you how it looks on the bus line, SPI bus. So there is MOSI, I'm not sure in English how to pronounce it, master out, slave in. Well, I don't like slave name, but I don't know who give this name, master device. But if not device, another microcontroller, then I don't know. So MISO is opposite part. Master sending, here is disabled NSS line. Let me see whether I have some of recording. Let me see, NSS line, yes. Here NSS line, so it is goes low, then communication, I'm sending byte 3 to register 3, and at the same time clock working for receiving part and MISO sending back. But because this is sensor which actually doesn't know what to send back, it waits one cycle, 1 byte, then it answers. During this answer we should to send some byte, dummy byte, so call it dummy or dummy, fake byte, in order to microcontroller to works. Then we pull out wire back to high voltage, so deselect. Sometimes some sensors can work in the case of more than 1 byte, not pulling, selecting wire back, NSS wire, then continuing if more bytes is about to receive. So this will be for next video. This part is just brief. What else specific? All pins except MISO should be configured like output, not push-pull, but alternate function push-pull, which means that outputs are with 2 transistors, but when not active, it can be like input, working as input. This is alternate function. 50 megahertz, depending of module which you use, you may choose 2 MHz, 10 or 50 MHz. I choose 50, I don't know, just for fun. Then we have clock, also alternate function, no reason. It may be classical general purpose output, but I found in documentation that it should be alternate function. Input is floating input without anything, no pull up resistor, no pull down resistor, and we have MOSI pin, which is alternate function as well. Not to forget that there is slightly confusing part in documentation about NSS pin. It says that we should to provide a separate pin on microcontroller, select chip, then send data. This one can work with this byte. We set this byte, this register, NSS line is enabled. This is if we want only one sensor. If we want to enable a second sensor, we cannot do that with the same wire. So usually for more than one sensor it is not used, or one device, no need to be sensor. Like in this case I have here transceiver STM32 and plenty of wires, which is half of wires actually logic analyzer. So master, selecting master. This is also important. Speed. Speed I'm using not lower speed, the most lower speed, but almost lower speed, because my logic analyzer is not that good on crashing if I put higher speed. Also clock, RCC clock should be enabled for SPI, and there is polarity. We have 4 choices, which means that when idle, clock can be low or can be high. MOSI and MISO also clock can actually not clock data can be high when idle or low. So we have 2 choices for clock and 2 choices for both of those. This is a little bit confusing, but after we enabling every, oh yes, before that NSS pin, since it is actually input on microcontroller, it should be pulled up with resistor. Somebody said that is good practice to use 1 kilo per volt. If we have 3.3 volt microcontroller, 3.3 kilo. I'm using today 2.7 kilo and there is no problem. Why is that? This is because security measure. If we have 2 masters, for example, this transceiver, this is not sensor, can be used by 2 microcontrollers. In this case, this wire can be shared from one microcontroller or other. If one microcontroller starting first, pull wire down, then another microcontroller feel that change, and if it is about to send data, it stops not sending data, immediately stops. For this reason, unlike I2C, which is line high by definition, or by resistor, or by device you power, this time we should to implement some resistor to pull line up. So for example, I should to make this case, this specific case, 2 masters, each communicating with this device, and when pull, who first arbitration, who first pull this wire, have right to communicate. Okay, I paused the video. I wanted to find this document, which is pretty much confusing. modes, RX only. We can actually pull data from other device only, not sending anything, if such device know what to send. In my case of this transceiver, I should to say command or register, and then this device sending back. So there is a little bit complicated behavior transmitting. If one case, in another case, there is plenty of things to cover. It looks simple implementation per one particular case, but there is many cases, so let's call it versatile case. Remain me later to cover also so-called bit banging or byte banging, where we do not use hardware. In this case, let's call it modem, although it's not modem. Hardware on microcontroller do everything. We just put data and microcontroller sending and receiving data, shifting and so on. Bit banging means that we using byte separating bit by bit and banging on the wire. For example, put one byte on one wire and then clock on another. Here we have specific part. Most significant bit is 1 or hexadecimal 80, which is, let me use calculator. If we have some data and we do OR with 80 equals, so this byte is 1, because SC4432 has specific 127 registers and copy of all registers for input. By copy means that this byte should be 1 to access this upper part. If we want to receive, then leave 0. So what else I forgot while configuring idle clock polarity. 8-bit or 16-bit, depends which device. In case of this transceiver, there is 8 bytes. We can set 16 bytes. MSB or LSB first. So this is together with polarity setting for SPI. I should next time to make more devices. I have hard time to find actually device sensor which has SPI, or there are all I2C. There exists I2S, which is very similar to this one, share the same registers, part of the register, not all. I2S is different than I2C. I2S means for sound, for stereo, for sound. For example, it's clocking out left channel 16 bits, then right channel 60 bits, and there are control bits. So SPI is good thing, it is fast. I2C is maximum, let's say 400 kilohertz, although it can work to 3.5 megahertz, I think. SPI can work up to, I think, 48 megahertz or so, 50 megahertz. Let me pause video. Okay, I found it. Diagram for SPI, shift registers and logic, plus data registers. And there is in the same time implemented I2S clock generator, which uses the same pins plus something extra. This is a little bit complicated. I have problem because I have no device to test to be sure what I'm talking about. So I will cover just SPI part. What did we forget? After we setting everything, if we writing, we should to initiate protocol initiate transfer by this SPA, this initiation, which if we select NSS enable, pulling wire down, then putting byte in data register and wait until flag takes transmitter buffer is empty. Then we send another byte. There is example in document for more than 2 bytes. I need only 2, so there is second byte. Then we should wait also to clear this register for next byte, but we have nothing. In this case, we should wait until microcontroller told us that it is not busy. And also in the case of short transmission, overrun over something, I'm not sure what, then we close communication. This waiting is good if we want instead delay, using delay to wait until process is finished to not making error on microcontroller. While SPI writing, it is also receiving, but we do not, in quote, pick up signals. No need to pick up. This is one way. There is many ways. There is master, slave, there is full duplex, semi-duplex, complication. I choose full duplex. This means that on 2 wires going data. Semi-duplex means that on 1 wire we're sending MOSI, master out, slave in, and this chip whatsoever answering on the same line. Clock is separate. Some device can work. This one I have not. SPI read, the same thing is here, enabling. Then we sending 1 byte and waiting until this register is clean. Then waiting whether it's busy, working, still clocking out bits. Then we're setting dummy byte. I'm calling that dummy, not my invention. Somebody put here, I don't know, FF, it is the same, doesn't matter, to recognize on logic analyzer. This byte is lost, but must be there, or else it will not work. Also we wait, but this time until is receiver buffer not empty. This means that we receive some data, then we reading this data. First data is also dummy read. We call it dummy because it is empty. In the case of microcontroller, it is probably not empty. The microcontroller depends, is preparing some data. In the case of sensors or some other devices, we asking, sending request, and we reading nothing, 0. Then after preparing data, we reading again. In meanwhile, also waiting for register to be empty, and finally close this. We can use global variable. In my case here, I'm returning R request, or I don't remember why using R. So it is integer in return. Input register, and calling this register to give me information what is in this register. In the case of writing, I have register and command. if you have more than one, in both cases, you can put command then length and for loop to count how much bytes will send. This will be covered next time. I want to show you something interesting similarity between I2C and the SPI protocol, at least in how it looks like. Sorry, message. Let me scroll down. We have here SPI and I2C. We have in I2C start condition. Here we have opening condition. I don't know how to SP enable. Also here we wait. In SPI on I2C we wait. Here waiting for start bit, whether start bit is going or some errors. In the case on I2C we have address shifted left by 1 bit and inserted 1 or 0 depending whether we writing or reading from this address. Here we have a little bit different configuration, but similarity: data waiting, and end here, end of SPI protocol. By means of end, it will release wire, it will go up again. This we have stop. So why I'm talking this? When you learn, for example, I2C, when you get familiar, this one is very similar complication as well. And when you have received SPI have a better protocol for STM32 at least. Here is complication about 1 byte, 2 byte. If you send 1 byte, it is different. Actually, if you receive 1 byte, 2 bytes or more. On SPI, it's just simple. Unfortunately, I did not put this one. Next time, in next video, I will cover how to implement reading more than 1 bytes. Also, yes, this module have 64 bytes of buffer, FIFO buffer, first in, first out buffer, so it can be filled at once. I'm happy to get this module working, this transceiver. It bothers me for many years. I got semi-working, but not good. So I rushed sending byte by byte. So pulling down wire NSS, sending 1 byte, pulling up, down, up, every byte. Instead, it is better actually to pull once and send whole 64 bytes at once, saving time, saving. I have something here. I have all the time interrupted by my kids asking in or out. I did not cover interrupt because at the moment it is easier to do without interrupt. Also DMA. I will leave DMA for later. It is very specific. So just briefly about this transceiver. Here is main program enabling serial interface, USART, SPI enable, and set module. Here is calculator for frequency and power. I did not finish calculation for data rate, for sending data rate, and management of type modulation. On-off keying, OOK. This one is GFSK, which means Gaussian filtering FSK, and ordinary FSK, which is a little bit wider. So all we have is listen radio. In this file we have here table, selecting table. Maybe it's possible to get some mathematics to shorten this code, but at this moment I want to point out that I'm using interrupt only for receiving from the PC over the USART. This is because if I do not, no matter how I wish to avoid interrupt, I must use, because I cannot make a loop in the same time receiving, then transmitting, then it cannot back to receive mode. There is so-called polling. When you're waiting, reading some pin, waiting for data, then acting. Interrupt, we can send data and wait interrupt to happen. Then we jump to interrupt routine, interrupt handler. This handler, I don't know why many people forgetting disable this interrupt. This I'm enabling only interrupt in the case that I'm sending data over the console, for example, to my receiver. Let's put something here, and you will hear on SDR receiver 20,000 characters, or a little bit less actually. So when I press enter, this is signal that I put all data and that transmitter can start. And here is some mathematics. So interrupt just doing this job. I'm not putting interrupt when I'm receiving data from radio and convert. This is manual task. I can do that, but I don't know. So we have here similar situation. Made mistake. I should on EEPROM. I made mistake about cases when we have buffer 64 in the EEPROM is 16 one page, actually one sending. There is buffer of 16. Here is buffer of 64 elements. In the case less than 64, then is one routine, one algorithm. If more, then we have the rest, and finally fraction. Actually, fraction is remaining. So we have, for example, in the case 12 bytes, we're sending only 20 bytes and returning. Let's say a little bit more than 64. We have main program which sends 64 and plus another part separately. So I made it completely not to sending 64 by 64 by means of manual separating. I got example exactly manually, byte by byte, putting into each register. I put this way that over the console I put text, and this algorithm separate text in into pieces of 64 bytes and sending. The same thing is when receiving, but in this case we have on this module or transceiver address 4B hexadecimal, which told us length of received message. I disable CRC error checking. There is other checkings, so I just print character by character on the monitor on the PC. This is that part, and other things are very complicated. I put here question marks because on documentation there is no explanation. Just put like that and forget. Okay. There's preamble, length register, and so on. I will not talk right now too much about this module, just to let you know that it works right now. Frequency. Oh, I did not I make a calculation for frequency. Let me find it. Here is all the way by manually putting one frequency, single frequency. When you program chip, it works on single frequency. Now we can choose this frequency and it will calculate for us. Here is up calculation, this one, and table of bands. Each band low part is each 10 megahertz, upper part is here, upper part is each 20 megahertz range. HB select high band, select 0 or 1 and some calculation. What missing here is calculation for baud rate, for how much I put fixed 9600 bytes per second or 9.6 kilobit per second. I should include also mathematics so that those registers are automatically something like on Arduino serial print, when you put serial begin and how much, how fast. What else we have here? In print message there is ordinary. I'm printing, not receiving from console, from monitor, but now I need to implement this. Ordinary no more than 256 bytes, but this time for this big chip I put buffer of 20,000 bytes. This doesn't work on blue pill on STM32 F103C8. There is some conflict, probably memory or something, so I put 20,000. You don't need this, but I just for fun put as much as possible. Maybe there is possible 30,000, but okay. I want to implement also file, sending file. If you want to communicate with somebody, also call sign when you want to select somebody separately or talking in group. This will be complicated. This is it for this first part of SPI protocol. I say protocol is complicated. This code I made is simple, but this is just small percentage of everything. So now let me see this module. When I starting, I have some control bits, control LED, this one lighting receiving, this one transmitting, this one is power on, and this one not working. There is generator inside. You can get 32.768 kilohertz for clock purpose, or 1 megahertz to 10 megahertz up to 30 megahertz. This is made because you can use this clock to power a cheap microcontroller, small microcontroller up to 30 megahertz, instead having separate clock on microcontroller. I disable this signal to avoid making noise. Oh, this antenna is terrible. Just don't use this antenna. And this, pardon, this LED is for transmitting. Let me transmit something. Now it will light differently. You can hear signal. This module is small and it has one big problem. Look this. Space between each needle is 1.27 millimeters, and like ordinary 2.54. Too small. But luckily there is adapter on eBay or probably on Bagu too. So what you need to solder this one together, and you have big pins for easy manipulation. Probably this board is actually made for implementing on another board for communication. Too much messing. Another board is SC4463, even more advanced chip, even more complication. RF69, I think, or 96, 69, which is pretty similar protocol like this one, different manufacturer. Talking too much, okay, people, headache, exploding. I need your feedback. Please tell me what you need first of all those combinations. I know that you will say first to operate with sensors, but if somebody wants to communicate over this protocol with another microcontroller, tell me and we'll go into this direction. On STM32 there is even better protocol. This is CAN, controller area network, which works even faster, but I have no idea, I did not cover it. It's just barely understanding SPI and I2C and everything else. Also I2S for audio purpose. This protocol is developed by Philips. I think that CD-ROMs, I'm not sure about Blu-ray, but CD-ROMs using this protocol, some digital audio devices. I say the same registers. The problem for me is that I have no any device for testing and for showing you how to implement in code. Aside CAN protocol controller area network, there is Ethernet protocol and USB. USB to me is a little bit difficult. Actually, everything is difficult when you're starting for first time. Ethernet too. You can plug your microcontroller into computer and have even faster communication between microcontroller and computer. Maybe between two microcontrollers. I don't know. I'm not sure. So that's it for now. Oh, before I go, I put all my codes about SC4432 on my web page, but did not put onto menu. It is uploaded, and here is everything you need. I will put a link in the video description. The problem is that I'm trying to learn Eagle to make some block diagram. I don't want to mess with pencil or whatsoever on paper. It's pretty ugly. So I will put a link. So if you know how to connect, how to read code, in each code there is a GPIO definition, and each definition says, for example, using A2 pin GPIO A2 and 3, 4, 5, 6, and I think 7. And you should have pin out of the chip. Ground SDN is not part of SPI. This pin goes up for, let's say, 1 second, then remains grounded, which tells chip to work. This is some kind of hardware reset. And IRQ, this is IRQ interrupt from chip telling us that also negative all the time. One negative means that when it is low, telling us that something happened. for example, received data or some error occur or something. N-cell, the same as NSS, but this is old names. From this is goes confusion. Clock, the same SPI. SDI is actually MOSI, master out, slave in. SDI means serial data input, serial data output, but in this case MOSI, MISO. Voltage on 3 GPIO ports, of which GPIO 0 and GPIO 1 is connected to antenna switcher and another ground, 2 grounds. So you can actually power it and enjoying. Here is code. Page is not finished. Just put something to so that you can begin to work. Okay, enough. Bye.